In this video, we will take a look at radicals and a few of the reactions that they undergo. Before we get into the details of any of the reactions and predicting products, I'm going to define several terms that we'll use throughout this video and all future videos. So first of all, a radical is an atom, molecule, or ion that has an unpaired valence electron. So far in all the videos, we've seen lone pairs in the sense that there's always two electrons together. Radicals are not like that. They only have one electron. They're lacking a partner. So by definition, that means that the atoms will be missing a octet. They will have a lack of an octet if they're a radical because they cannot have an even number to have that unpaired valence electron. It will always be odd. So here's an example of a radical. I have the hydroxyl radical here. So we have an oxygen bound to a hydrogen, the normal hydroxyl group, and then two lone pairs and one electron that is unpaired. So notice the unpaired valence electron, that is this one here at the top. And also notice that there's a lack of charge. So if we remember our formal charge counting rules, we count all electrons as one, the total that they are, and we count all covalent bonds as one as well. So using that rule here, we have 5 electrons, 2 of them are in pairs, 1 is unpaired, so that's 5, plus 1 from here is 6. Then we compare that value to the periodic table, which tells us the number of valence electrons that oxygen wants to have to be neutral. We'll see in the periodic table that oxygen is in group 16, which means a neutral oxygen would have 6 valence electrons. So we take the actual electrons that there are minus the electrons that it would want, which is 6 minus 6, and we get a charge of 0. That is why this is neutral. So radicals don't necessarily have to have a charge, but they can. That's why some radicals are ions, but it's not a requirement of radicals. But notice also that this oxygen lacks an octet. It only has 7 electrons because when we're counting for our octet, we count the covalent bond as 2 electrons because these are being shared. So therefore, this OH radical is certainly less stable than the if this was bound to another hydrogen, like in water, because then the oxygen would have its full octet with the new bond. So that is radicals. Next thing we'll talk about is homolytic cleavage. So this is a specific type of bond breaking in which one electron is transferred to each atom that is involved in that bond. So it's homolytic because homo means same, lytic means cleaving, it means breaking. So homolytic means same breaking, and then cleavage is the bond breakage. So this is the same amount of electrons are moving to both atoms involved in the bond. So then if we look at an example here, I have Br2, this is molecular bromine, and the homolytic cleavage would be one electron going to this bromine, one electron going to this bromine. Both electrons are coming from this bond. So the half arrow means that one electron moves, and the other half arrow is the other electron. Notice that this is different from everything we've seen so far. We've seen the double-headed arrow, which means that 2 electrons move with that arrow. So here, 1 electron is going to this bromine, 1 electron is going to this bromine. We have broken this bond. It's no longer there, so the products are a bromine radical and another bromine radical, where this blue dot is the radical from this arrow, the electron from this arrow forming the radical, and then this blue dot is from this half arrow here. The next thing we'll talk about is heterolytic cleavage. This is this type of bond breaking in which both electrons involved in the bond are transferred to another atom. So this is the much more typical type of bond cleavage that we've already seen in all of the other videos, and it involves the double-headed arrow in which the 2 electrons involved in this bond are moving to this bromine. So in this case, we have a hydroxy ion. The negative charge on the oxygen is coming here to this electrophilic carbon, creating this new bond between the carbon and the oxygen, this blue bond here. And then the bond that's broken is this carbon-bromine bond, and the electrons involved in that bond, both of them, move onto the bromine and make a negatively charged bromine. Notice how this is quite different from radical formation because we are using both electrons in this case, so everything has an octet at all times, and that's why this is much more common to occur, but homolytic cleavage does come up, and since I defined homolytic, now you know that heterolytic is the more common type that we've seen throughout other videos without defining it formally here, like in this case. So now, the next thing we'll talk about is bond dissociation enthalpies. This is the energy required to cause homolytic cleavage of any given bond. The notation is always delta H naught, which is just the abbreviation for the change in enthalpy of this of any bond that we're talking about, any bond formation. So here, an example, a general example, is the cleavage of methane. So since this does not happen naturally, this cleavage, this homolytic cleavage, there must be some input of energy that causes this bond to break and put one electron onto the hydrogen and one onto the methyl group, the CH3. So when that happens, you form the methyl radical and the hydrogen atom, which is the hydrogen radical, and the amount of energy required to cause this homolytic cleavage was 105 kcals per mole. Now that's great, but why are we interested in the amount of bond energy? You can imagine if you know the amount of energy that it takes to break a bond, you can create a table of relative energies of the intermediate and determine which intermediates are more stable than the others because it took less or more energy to make that intermediate. So in essence, we can use bond dissociation enthalpies to predict and understand the stability of the radicals that form after the bond dissociates in this homolytic manner. Okay, now we will look at several specific bond dissociation enthalpies. Again, they're denoted delta H naught. So here, the first one we'll look at is an allylic hydrogen. So recall that the allylic position is a carbon adjacent to the carbon-carbon double bond. So here we have a carbon-carbon double bond. This is a carbon adjacent to that pi bond. That is what we call the allylic position. And we have a hydrogen bound there, so this is an allylic hydrogen bond cleavage. So when this bond dissociates, we form the allylic radical, the allylic carbon radical with the unpaired electron on the carbon, and then a hydrogen radical. And this takes 89 kcals per mole. And we'll go through several of these types and compare the relative stability of the radicals formed by the energy required to break the bond. So here, this is 89 kcals per mole. This was significantly less than the larger than 100 that we had for our methane group that we initially showed in the first example. So let's compare this now to a benzyl group. Again, homolytic cleavage. At this position, we make the CH2 radical here at this position. And that is what we have here, the benzyl radical plus our hydrogen. Now, this is 90 kcals per mole, so the allylic radical and the benzyl radical are comparable in energy. They're about equally stable. Next, we'll look at a T-butyl group. Again, the homolytic cleavage onto the carbon, forming the carbon radical and the hydrogen radical. So this takes 97 kcals per mole. So again, relatively stable compared to the methane that we started with, but still the allylic and benzylic radicals are far more stable because it took much less energy to break those bonds. And then move down to isopropyl. This takes a little bit more energy than the T-butyl group. And here we have an ethane group, again, increasing in the energy required, so the radical is less stable. Here we're at our methane group, 105 kcal per mole. And then lastly, we have our vinylic radical. This is the least stable radical of all that we've explored here and requiring 111 kcals per mole to initiate this homolytic cleavage. So the vinyl carbon radical, similarly to the vinyl carbocation, is the least stable of the options that we have looked at. So you can use these bond dissociation enthalpies to give a list of the relative stability of the radicals, like I alluded to as we were going through. The more energy it takes to form that radical, the less stable that radical is because it took more energy to reach the transition state to make the intermediate. So here we have our list. So benzyl is about the same as allylic. This is greater than tertiary, which is greater than secondary, and greater than primary, which is greater than methyl, and lastly, vinyl. So this is basically the exact same that we see in carbocation stability with small differences in the benzyl and allylic positions, but the general trend is the more substituted the radical, the more stable that radical is. And the most interesting thing about this relative stability of radicals is that we can use this to predict the major products of the radical reactions. We do this through a mechanistic approach, where if we're going to form a radical to make the product, then if we know the most stable radical, then we can predict the type of product that will be formed. Because if you know the most stable intermediate, the reaction will go through the most stable intermediate, and then it'll make the product that is consistent with that intermediate. So this is a very valuable tool, and it's useful to understand that it comes directly from the bond dissociation enthalpies, because there will be reactions that you haven't seen before where you can use their bond dissociation enthalpies to predict the products if it's a radical mechanism, if it's a radical reaction. All right, so here we have an example. So using what we just talked about, the relative stability of the radicals, we can predict which one of these is the major product and which one is the minor product. So we haven't looked at the mechanism of these radical reactions yet. I'll save that for another video as it's quite involved, but we can know that this is a radical mechanism, which means that we're going to form radical intermediates. So in order to form this product, we would need to form this radical intermediate. If we're going to form this product, we would need to form this radical intermediate. Now, based on the rules that we just looked at, we know that this is a secondary radical, whereas this is primary. And we know, again, from the bond dissociation enthalpies, that secondary radicals are more stable than primary radicals. So because of this, this intermediate is far more stable, and therefore the reaction will go through this intermediate and form this as the major product. However, it's not impossible for this to occur, so this will form and it'll be the minor product. So again, we can use the relative stability of the radicals based on the bond dissociation enthalpies to predict the major product. For the remainder of the video, we'll look at several examples where, again, we can use this bond dissociation enthalpy idea to predict the major product of the reaction. So here, we need to consider all the possible radicals that can form. And there are many that are equivalent to each other. So if we consider this position, if we're going to make a radical there, it would be primary, here secondary, here tertiary. So let's draw those three options. Here's our tertiary radical. Here is a secondary radical. Here's a primary radical. Now, notice the radical could form at these methyl groups, and that would be primary radical as well, but that's going to be about the same stability as this one. So I'm not going to redraw them just to avoid clutter, but here these are representative of the three types of radicals that could form in this reaction. So here we have a tertiary, which is by far more stable than the secondary, which again is more stable than the primary. So then if we use this as our major product former, the major product is going to have the bromine at that position, at the carbon that is the most substituted. So our major product then is this one. You can also form a non-negligible amount of the secondary, and then there'll be traces of all of the primary products. So that would be if the bromine is at this position or at the other two methyl positions, which again, I'm not going to draw just to avoid the clutter. But if the question was, what are the major products? This would certainly be the major product. And I would say that this is your minor product and that there would be traces, if at all, of the primary product. So if I were answering this question on an exam as a free response, I would put these two and I would include major and minor for the tertiary radical and minor for the secondary radical. Here we have another example, again, predict the major products. So here we have a cyclic structure, but this doesn't really change the approach. Again, we're looking for what's the most stable radical. So if a radical forms here, it would be tertiary. Anywhere else in the ring would be secondary, and the methyl group here would be primary. So let's compare 3 of those that are representative. Here is the tertiary. Here is the secondary, one of them, representative of any. If the radical were to go here, here, anywhere else, that would be the same, that would be equivalent. And lastly, it could go here, which is primary. This is certainly going to be the least likely to happen. So here's our tertiary radical. That's more stable than the secondary. It's more stable than the primary. So our major product is certainly going to be the going through the tertiary radical. And again, we're using chlorine in this case. It can be any halogen. Chlorine and bromine work the best. There is instances of other. Fluorine is extremely reactive and unsafe, so it's usually not used in chemical reactions, but chlorine and bromine do this the best, and they're the safest options to accomplish this, so you'll see chlorine and bromine. There are slight differences between the halogenation process and bromination and chlorination, and we'll explain that in a different video, but you can do this type of chemistry with chlorine or bromine. So this is a major product, and the minor product is going to be the one that forms through the secondary radical. Now, notice there could be a lot of minor products here, because you could form the radical here, 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 or here. Any of the positions in the ring would form an equally stable radical, essentially. So you could form a bunch of the minor products. So by far the major product is going to be this tetrasubstituted carbon, where the chlorine makes the 4th substitution. This is the last question for this video, and this is tying a couple ideas together from the previous video and the previous chemistry that we've explored. So first, we're just asked to predict the products. There's going to be 3 answers that we have to give here. First of all, we're doing a basic chlorination, radical chlorination of methane. So what this is going to do is make the chloromethane. So A is going to be ClCH3. We've created this carbon-chlorine bond. Now look at B, or the formation of B, this reaction. We have a terminal alkyne. Remember that these are acidic protons. And we have amide. Amide is an extremely strong base. So this is going to attack the acidic proton and create this carbanion. So B is the carbanion, this CH3 alkyne carbanion. And there's going to be sodium counterion there. And now lastly, we're mixing A and B. We're mixing A and B together to form C, right? So remember, the purpose of deprotonating alkynes is you turn them into a good nucleophile and a good base. But in this case, it's going to function as a good nucleophile because we have a primary haloalkane. So now, if we do this reaction, we have a good nucleophile in this carbon nucleophile here. And we have a good electrophile in this dipole moment that we have across this bond. So our carbon is partially positive charged. And then, so what's going to happen is this will function as a nucleophile, and it will attack the carbon and then cleave heterolytically this bond, this carbon-chlorine bond, cleave the electrons onto the chlorine. So what you get is the creation of this new carbon-carbon bond between the carbanion and this electrophilic carbon. So the final product in this case is methyl group, internal alkyne, bound to the CH3. And then as a byproduct, we have sodium chloride, because we dumped chlorine as a leaving group. So this would be a Cl negative, and then we have our original sodium that I should have included here to balance this charges that I show in B. That is where this NaCl is coming from. So that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a question, feel free to leave it down in the comment section below and I'll get to it as soon as I can. But with that, I hope you have a good day and I'll see you in the next video.